Before we begin the new material, I thought I'd back up to the last two definitions we were discussing at the end of our last class. So in lesson 1.3, we are focusing in on angle pairs, or lesson 1.2, focusing on single angles. So in lesson 1.3, we've talked about linear pair of angles, supplementary angles, vertical angles, and complementary angles. So the last two definitions we discussed were supplementary, which is a pair of angles that have a sum of 180 degrees. The angles don't have to be attached as long as the two angles add up to 180. So you could select any two angles in a square, for example, or a rectangle, and those two angles would be considered a pair of supplementary angles because any two angles add up to 180 for those two shapes. But if the two angles are connected, if they do share a common side, as in the first and fourth illustrations, those supplementary angles have a special name, and they are called a linear pair of angles, which we discussed earlier in this handout. Complementary angles is a pair of angles that have a sum of 90 degrees. And again, like supplementary, they can be attached, like in illustration 1 and 3. Or they can be separate angles. Again, it doesn't matter either way. What's key is it's a pair of angles, and the sum is always 90. So we're going to just open up with a general question. How many triangle and quadrilateral names do you know? And I like to list them. I'm not going to go through all of them at this point. That will come up in the next couple of lessons. But I'm just curious how many of them you actually know. So when you're finished with that, I have a PowerPoint presentation that I'm going to be using to talk about the idea of a polygon. So I'll give you a few minutes to do these names here, and then we'll continue with the polygon. So when discussing polygons, we're going to go through a presentation here to talk about what it is and what it is not. So once you look at each shape, I'll give you a couple seconds for you to think about it. Would you say this is a polygon or not? I'm not in class to have this conversation, but I will at least talk to you about what it is and what it isn't. So this first one here, is not a polygon. Polygons have to have a region, as an interior region. So, building upon that, this would also not be considered a polygon because, again, it doesn't have that closed region. So this one would be considered a polygon because we do have that closed region. It's of all of our polygons, it's the one with the fewest number of sides, which we call a triangle. For the same reason, this one would be considered a polygon. It does have a closed region. Again, it's a triangle. And same for this one as well. How about this one? So this one's a no. It does have a closed region, but one additional thing about a polygon that was not part of the first 5 I talked about is the fact that the polygon is actually made up of straight sides. So that top part there is curved, which actually makes it what's called a sector. This is not a polygon because you have a curved edge. And this one is a polygon. It does have a region, and all the sides are line segments. Same thing for this one. It's a closed region made up of sides that are line segments. So the last one, it does have that closed region, but the two ends are not straight paths, which is the reason why it's not a polygon. So this one is all sides are segments, one region. Same thing. So this one's a no. It does have the one region, but it's made up of one path, and it's a circle. This is a no because the bottom edge is rounded, and again, it's not made up of just line segments. Same thing with this one. Again, you can look at that as the bottom is like an illustration of a cylinder, or just made up of kind of an oval with like a rectangle, sort of like a rectangle in the middle, but it has a bunch of curved edges. The top, right, is a no. It is made up of line segments, but has three regions. Kind of looks like a solid, an illustration of a solid. This would be a yes. One region, all made up of line segments. Same thing. It's one region made up of line segments for its edges. This would be a no. This would be a yes. So, like, you'd write down your answers for these 5 here and tell me if you think which ones are polygons, which ones are not. Okay. So hopefully you selected the first, second, and the fourth as polygons. The third one doesn't work because it has 3 regions instead of 1, and the fourth one doesn't work because it's made up of curved edges. So take a moment and think about how you would define a polygon. It's a lengthy definition, so you may want to write yours down in pencil and then adapt it based on our conversation we're going to have here. So I would suggest turn the video off and write down your definition, maybe check it with 1 or 2 people sitting close to his partners, and then turn the video back on. So a polygon is a single region. And it's a single closed region. That has line segments. Line segments are connected to the endpoints. Of other segments. So these segments, we actually have I give it a different name to when we talk about these shapes to kind of clear up make sure these segments are connected in the right way. We call them sides. So basically, each segment is connecting to 2 different sides. So the endpoint of one segment is connecting to an endpoint of another segment, and same thing with the second endpoint of the original segment is connecting to the endpoint of a third segment. So those segments are connecting endpoint to endpoint, and those segments are what we call sides of the polygon. So how many of the special polygon names do you actually know? You need to know all the names for 3 through 12, and then we do have a generic name that we give for the n. So complete those and then turn the video back on when you're ready. So save a little time. I went ahead and typed in the names. But hopefully the first couple you know, the triangle and quadrilateral. Many of the special names are based on polygon. So gon means sides, so you'll notice a lot of these end with a gon. And then the beginning of it's a prefix, and that prefix is an indication of how many sides. So penta means 5, so pentagon is 5 sides. Hexa or hexa means 6, so 6 sides for gon. Hepta, 7 octa, 8 nona, 9 deca, 10 undeca, and it's 11, and dodeca is 12. Once you get past 10, going from 10 through 19, 11 through 19, they generally have 2 prefixes put together, so un meaning 1, like for unai or uno, and deca meaning 10, so it's basically 1 plus 10 makes the 11. Do means 2, deca means 10, so they do 2 plus 10 makes the 12. Trideca for 13, and so on. The generic name we use is n-gon, n meaning any number of sides, again, gon meaning sides. So one of the things we do a lot in geometry is to name shapes. So for example, we can name this pentagon A, B, C, D, E. If I'm start at A and going counterclockwise, I can start at D and go clockwise, go from D to C to B, A, and E. So what you want to do when naming something, you just choose a vertex, you go clockwise or counterclockwise, and you name the points in order as they come. So for example, triangle, I can start A and go clockwise and call that triangle ACB, or I can go counterclockwise, start at A and call that triangle ABC, and both names are perfectly acceptable. So Dras here is a list of other names for the triangle. And then if you recall back in lesson 1-2, we talked about this idea of a congruence, and we have a special symbol for that. So if you could draw the symbol, and what does the symbol actually tell us? I mean, why do we have this special symbol? When you have answered both problems, please turn the video back on. So for the triangle, you basically have 2 directions you can go from each vertex. So there are 2 different names for using A as a starting letter, 2 different names for starting with B, and 2 for C. So these are the names we could have in addition to the triangle ABC. The symbol, the congruence symbol, looks like this. The curved part of the symbol, what that represents is same shape. We use that single symbol when we're talking about similarity of shapes. Shapes can have the same shape, but not necessarily the same size, and that's why the equal sign is so important for congruency, because not only are the shapes the same shape, but they're also the same size. So congruence is probably one of the biggest topics that we spend a lot of time talking about in geometry, and we use different ways of trying to illustrate or define congruency, and transformations is one of those. Transformations being like reflections from rotations and glides or translations. Euclid used the term superimpose. And so the idea of superimposing is you took one shape stuck on top of another shape, and if they match up perfectly, then we can say the shapes are congruent. So for example, angle P would match up with angle E because they both have 4 tick marks, as well as C and S match up because they both have single tick marks. So when you superimpose one shape, everything should match up. The angles should match up based on the markings you're given. So we're going to have some problems here for you to look at where you're trying to decide things are congruent, and if so, what would be the order of the letters, and the letters do matter. So going back to this screen here, angles C and S are the same position because they both have the same number of tick marks. That was also true for P and for E. So go ahead and complete the last problems. So this will be the last answers for this video. So